In this exercise, we will be converting among the three numeral systems, the decimal, the hexadecimal, and the binary. To assist in the process, if we look at the right-hand side, this is the table that describes the main fundamental conversions. If we look at the hexadecimal column, you can see that one digit can represent 16 possible values by adding the A, B, C, D, E, F to the existing 10 numbers. In order to make this equivalent in binary, 4 bits are required. 2 to the power 4 will give us also 16 possibilities. Hence, converting between hexadecimal and binary is relatively straightforward. And that's why hexadecimal has been adopted in some programming languages. If we start first with the 64 decimal, in order to convert it to hexadecimal, one common method is to divide the decimal number by 16. We treat the division as an integer division, and we write down the remainder. The hex value at the end will be the sequence of the remainders from the last to the first. So, 64, we divide this by 16. Here the answer is here the first remainder is 0. Then we take the 4 again and divide it by 16. We need to repeat the steps until the result is 0, which is the case here. So the answer here, or the digit sequence of the hexadecimal number, will be from the last to the first. In order to find the binary number for this hexadecimal number, as we discussed before, each one digit in the hexadecimal is equivalent to a 4-bit equivalence in binary. Now, this 4-bit is normally called a nibble, or half byte, or semi-octet, or a quad bit. Doesn't matter, but the first digit in the hexadecimal, which is 0, actually is equivalent to a 4 zeros. And number 4 is equivalent to 0010. Let's do the same thing for the 128. 128 divided by 16. This is 8. And the first remainder is 0. We treat the division as an integer, so we throw away any decimal points. We take the 8 again, divide by 16. Here the integer is 0. And the remainder is 8. We write the hex value. It's the digit sequence of the remainders from the last to the first. To find the binary equivalence, again, we can use this table. So the first digit in the hexadecimal part is 0. This is equivalent to 4 zeros. And the 8 in hexadecimal is equivalent to 3 zeros and 1. So let's do the third one. Here we have a hexadecimal number that we would like to convert maybe first to decimal. To do this, we will take the first digit, which is the F, and multiply it by 16 to the power 0. And we take the second digit and multiply it by 16 to the power 1. Now remember, the letter F is equivalent to 15 in decimal. This means obviously anything multiplied by 0 is 0, so the answer is 15 in decimal. In order to find the binary equivalence of this hexadecimal number, again, if we look at the table on the right hand side, we will find that the letter F is equivalent to 4 ones. And 0 is equivalent to 4 zeros. Similarly, we can find the double F in decimal by taking the first digit, which is the letter F, which is equivalent to 15, and multiply it by 16 to the power 0, added to the second digit, which is F, which is also 15, multiplied by 16 to the power 1. Simply add. This is 240, and this is 15 times 16 to the power 0 is 15. Adding those numbers will lead to 255. Similarly, straightforward, we can find the binary equivalence. We know that each letter F can be represented by 4 ones. Now let's convert the 169 to hexadecimal. In a similar way, we need to divide the decimal number by 16. And we treat the division as an integer division. And don't forget to write the remainder. The first remainder here is 9. We have to repeat the process until the result is 0. The second remainder is 10. The hex value here is the digit sequence of the remainders from the last to the first. Now 10 in hexadecimal is equivalent to letter A. And 9 is 9. And once we obtain the hexadecimal equivalence, we can convert this to binary straight away using the table shown on the right. Number 9, if you notice, can be represented by the half byte 1001. And the letter A is equivalent to 1010. Let's do the 1084. 1084 in decimal. In order to convert it to hexadecimal, we'll divide it by 16. Again, we treat the division as an integer division. We repeat the process until the result is 0. This is around 67, and that will give us 1072. So the remainder here is 12. We take the 67 again, divide by 16. This will give us around 4. This is 64. Remainder 3. Take the 4 again, divide by 16, 0, remainder 4. So the answer here is 4, 3, and 12. Now 12 is equivalent to letter C. Similarly, in binary, the letter C is equivalent to 1, 1, 0, 0, and 3 is 1, 1, 0, 0, and the digit 4 is equivalent to 0, 0, 1, 0. The following number is in hexadecimal format, so 3D is equivalent to the letter D is 1, 0, 1, 1, and the letter 3 is 1, 1, 0, 0. In order to convert the hexadecimal 3D into a decimal number, we take the first digit, which is D times 16 to the power 0, added to 3 times 16 to the power 1. Now the letter D is equivalent to number 13. Times 16 to the power 0 plus 3 times 16. This is 13 plus 48. 61. Now we have a binary number, and we need to convert this back to hexadecimal and decimal number. If you divide this into a 4 bits each, you will find that the first 4 zeros equivalent to a 0, and the 4 ones equivalent to a letter F. This is the hexadecimal equivalent. The decimal equivalent can be found, as we have done previously, by taking the first digit times 16 to the power 0 plus F times 16 to the power 1. The letter F is equivalent to number 15. So this is 240. Similarly, if we look at the second binary number and divide those into 4 bits each, you will find that the first one, 0101, is equivalent to letter A. And the second one is 4, and the third one is 1. So this is the hexadecimal number 14A. Now the decimal equivalent can be written as such. We take the first digit, a times 16 to the power 0 plus 4 times 16 to the power 1 plus 1 times 16 to the power 2. Now letter A is equivalent to 10. So 10 times 16 to the power 0 and so on. So this is a 10 times 1, so that's 10. 4 times 16 is 40 and 24, 64. And 16 squared, 256. Adding those together, we get 330.